Welcome everyone to the machine learning meetup in person, third one since the pandemic. So we haven't run anything in this venue before, so we're really excited. And thanks so much to Meng Group for sponsoring and hosting today. So we have Meng Fang from the University of Liverpool giving us a talk today. And after the talk, there will be beers and some pizza generously provided by Meng Group. And yeah, we'll finish up at around 8 o'clock. I think we need to leave the building before 8 o'clock. So this, if you've not been before, this is really a kind of discussion group. So Meng will be leading the discussion, but it's really a space for any of us to contribute whatever we want and ask as many questions as we like. It's really very informal. You can ask anything you want. We don't like to have loads and loads of follow-on questions, but you can really ask anything you want. The most basic to the most advanced questions are very, very welcome. And then during the drinks, it's very, the principle is you can just walk up to anybody and just say hello, and that's the idea of the drink session. So it's really, really friendly, and the convention is just walk up to a stranger. So thanks again for coming. Thanks to Meng. I think we'll get going now, Meng. The best thing is for the QA to happen at the end of your talk, I think. So Meng will give a talk for about half an hour. Then we'll have the QA, and then once we're finished and we've got no more questions, then we're going to have some beers. So thanks to Meng.
Hello everyone. Thank the London Machine Learning Group for the invitation, and thank Martin. And thanks for having me here today. So I'm Meng Fang, and I will talk about my recent work, large language models, Neuro-symbolic reasoners. So today, first, I will introduce the background. Test worlds, particularly test-based games. And then I will talk about language agency, including knowledge graph as memory, language model can be decision-making assistant, and finally, I will talk about large language models, Neuro-symbolic reasoners. And finally, I will provide summary. So similar to our human beings, language agents can interact with external worlds. For example, in simulations or games, agent can interact with the environment while language to collect observations, to solve tasks, and to achieve some goals. And in our real world, imagine that in the future, we will have robots, right? Actually, recently, we also already have some very awesome, cool robots. And the robots should understand human language, communicate with human, and also help solve some tasks just based on instruction from humans, right? So we can see that for a language agent or language agents, the agent needs to understand how the world works, and the agent should be able to do reasoning and planning, and the agent can be driven. The agent can be driven by goals and tasks, and the agent can do can make decision by itself. And my research focuses on these areas. In my research, we consider test-based games. So in test-based games, similar to any other games, the difference is everything is a test. Observation is a test. And action is a task. So imagine that if you play the game, so when you say observations, your input is just a natural language like go west. So imagine that now you developing agents that can play the game, the test-based game. For the agent, its observation is also a task, and the output of the agent or the action of the agent is a natural language like go west or go east. So you can see that the test-based games seems to be very simple, right? However, it's like a small world. We develop test-based games to mimic the real world, and then we can develop excellent or awesome agents to play a game, to show the capacity of the reasoning and decision-making of the agents. So you can see that in the test world or the small world, the agents need to do reasoning and make decisions to solve some tasks. And for the observation and then the agent actions from agents, this process actually is repeated. It's similar to any other computer games. So actually, to build an agent for test-based games, there are a lot of challenges. You can say everything is a test, and actually the test has a complicated structures, and there are also in the game there are also a lot of puzzles that need to be solved by the player or the agent. So we can say there are multiple challenges, including to develop an agent. So the agent needs to understand language, and the agent needs to learn how to represent the world, external world, and the agent needs to do reasoning and decision making when it interacts with the test world or the external world. So my work is that we consider test-based games as a reinforced learning problem. So in a reinforced learning framework, at each time step, the agent receives a state from an environment, and then the agent takes action, and the action will be applied to the environment. And then the environment will return a reward to the agent. And at the same time, the environment changes current state to the next state. This is the basic reinforced learning framework. And the process is repeated. So again, the agents now have a new state, and then the agent can take a new action, and then the environment changes from current state to another state. And then again, the agent receives reward and a new state. So this is a repeat process. And as I mentioned, we formalize the test-based games as a reinforcement problem. Actually, it belongs to partially observable Markov decision process. So you can imagine that in a test-based game, for a player or an agent, it just receives partial information of the test world, right? It cannot know everything. So when time goes and the agent receives more and more information, and then the agent can make smart decisions based on the more and more information, right? So this is partially observed setting. And we also follow the basic reinforcement learning framework. So the objective of the reinforcement learning based agent is still to maximize the cumulative discounted reward. So in the games, the agent has to understand the world, right? So there are two problems for the agent: how to construct knowledge based on the game, based on test-based game environment, and how to do reasoning. So firstly, we built a knowledge graph to represent the world, and we use it as a memory of the agent. So you can say that when the agent interacts with the environment, the agents receive new information from the game environment, and then the agent, then here we use a knowledge graph to help the agent build a memory or understanding of the world, test the world. So you can see in the knowledge graph, it has entities, so like locations, like living room, and the connections between entities and the entities and the player. So you can see that actually the knowledge graph can represent a lot of important information from the test-based games. And we also use multiple subgraphs to represent different types of information. For example, one subgraph maybe just represent the recent updated information, and one subgraph just represents the locations. In this way, using a knowledge graph and subgraphs, we help the agent build the memories and the understanding for the texture for the text based games, the texture worlds.
What's a partial
Partial Thanks for the question. Imagine that if you play the game, so you can interact with the game, right? So when you take actions, the game return some observations. So the observation actually is not the full game, it's just a part of the information from the game. So that is a partially observed. It's like you communicate with a robot, and then when you ask something, the robot provides something, but you don't know full knowledge of a robot. So that is partially observed. So in the game, so the agent always receive information after it takes actions. So the information is just about the current state. It's not the full information of the game. So just about current state. So so we have a knowledge graph to represent the world, and we also use subgraphs to help the agent build memories and understanding of the test world. Then we use graph neural networks to do reasoning. So we use graph neural networks to encode these knowledge graphs. Based on the knowledge graph, as I mentioned, we also divided our knowledge graph as multiple subgraphs to represent the different types of knowledge. So at a high level, for the high level decision process, we use the full knowledge graph to calculate attention score. So the attention score is based on the full knowledge graph. on the right, the low-level decision process, we use the subgraphs to calculate the attention score. So at the low level, the attention score is based on different types of the knowledge graphs of the knowledge. And then we use the two attention scores to align the decision making of the agent to the knowledge graph. Let's see some results. So SHA-KG is our method. So our method works better than others, especially the state-of-art KG-A2C from Caltech, from Georgia Tech. And we can, according to the results, we can say different types of knowledge subgraphs actually are useful for decision making. So just now, we use knowledge graph to help the agent build the memories and understanding of the external world. And the goal here is that we want to use this memory to help the agent make better decisions to improve performance. So question is performance everything when it comes to the human-like system? So my answer is no. So for agency, we also need to consider morality. We found that actually in some test-based games, there is a moral dilemma in test-based games. For example, in some games, we found that if an agent kill lizard, then the environment gives the agent a positive feedback, like reward 3. And in some games, we found that if the agent hurts someone or some other NPC, then the agent does not receive any penalty. So based on these immoral behaviors, we think the agents should not just consider performance, but also should consider morality. So the question is how to revise these immoral actions of the agents. So our method is considering morality, and we have a moral awareness adaptive learning methods. Our method has two policies. One is task policy, so that is the goal is to have good performance. And another is a moral policy, so the goal here is to make an agent have moral actions. And then we consider both of them. So we have a mixture policy, and we use a parameter to balance the two of the policies. So for the task learning, you can say given current observation from a game, and our task policy can make decisions. And so this may be similar to the work I just mentioned now. I just mentioned there can be a reinforcement methods. For the moral policy, now the moral policy will consider the historical data and then make decisions. So the question is, how can we learn a moral policy? So our solution is that for the morality learning, we collect data from a game. So we collect data from a game, we build a data buffer, and then we use a common sense model here. We call it a common sense player. to enable the data. So given the data from the game environment, we can use a common sense model, which is a pre-trained model. We can label this data, and we can know which data is moral and which data is immoral. And then we can train a non we can use the properties from a common sense prior model, and then we can module the data, the language from the data buffer with the properties that considers the morality, and then we can build a language model based on the data with the morality labels, and then our morality policy actually is a language model-based policy. And let's see some results. So our methods is a mixture policy. It considers both task policy and morality policy. You can see that our performance, our methods works well, right? And you can see the competition percentage is also very high comparing with other methods. So it shows that it's possible to maintain morality while also preserving the task performance. So, please.
Sorry, okay. How do you calculate morality score? And why is human expert scoring the highest? The morality on that.
Thank you for the question. So for a morality score, the morality score is based on a pre-trained common sense model. So some researchers already provide a pre-trained model that was trained on some moral data. This moral data was annotated by experts before. So we use an existing common sense model to enable the data from the game. And then in this way, we can quickly have the moral score for the data from the game. So now we can easily to charge the data from the game, which actually is observation action pairs, which one is bad and which one is good.
So those are labeled by humans.
This label, originally the data is labeled by humans, but that data is not game data. It's just like a web page or some standard language data, test data, and this data was labeled by experts. So here we use the model that is trained on the existing moral data to the data from a game. So this is how we label the data from a game automatically. So just now we discussed for agent, we want to improve the performance, task performance of the agent. So we want to build a memory for the agent. So we consider using knowledge graph and subgraph to represent the different types of information. And then we consider morality, right? Because we think that a good agent is not just about task performance, but also about morality. And now we are considering symbolic reasoning. So the question is, can large language models do symbolic reasoning? So in this work, we consider the tool using for the agency. Large language model are very recent, very popular, right? Actually, recently there are a lot of language models from the big companies like Llama 2 from Meta and GPT 3.5, GPT 4 from OpenAI, right? So I guess here, I think most of you may use the ChatGPT, right? So for me, I use every day. It's very, very cool application. So we have already seen that large language models has been applied to many applications, right? For example, some basic tasks like text generation, classification, question answering, translation, and diagram generation, to some complex tasks like writing a sentence, content and idea creation, generative assistance and search assistance, data extraction, conversational search, code developer, and so on. So the question is, can large language models do symbolic reasoning? So at first, I'd like to briefly introduce the symbolic AI. So symbolic AI actually is an important area in the AI. For example, here, for symbolic AI says the apple is a graph of roots. So you can see here, the apple is a fruit, and it could be a green or red, and then the shape is round, etc. So you can say symbols here are actually very cool, right? Because this is exactly how our brain works. Another example is about math. So we can say we can use symbols to represent a math problem, and then we can use math tools to solve it. So in symbolic AI works by processing symbols. So these symbols can represent objects and concepts, and then it also can represent relationships between these objects and concepts. In the real world, we humans use tools like calculators. So the question is, in test-based games, can we have similar problems? For example, here for some games, the agent also needs to do math. You can see here, this is actually a math problem. So how can an agent solve this math problem? So what we want is that we want the agent that can use calculator. Here we also say symbolic modules, except that the agent can interact with the environment. The agent should also use symbolic modules. So the agent should understand the language and use the relevant tools for solving a problem. And the key here is that how to understand language and translate the language to symbols. There are also other symbolic tasks like map reader, sorting, TWC, which is about knowledge base. So for Iris Mac, we can use the agent can use calculation module, and for map reader, the agent can use navigation module, and for sorting, the agent can use a sorting module, and for TWC, the agent can use knowledge base module. So for example, if an agent provides input like about 87, to the calculation module. Then the calculation module or the tool directly return the result 56. So here our idea is we want to use large language models as neurosymbolic reasoners. So previously, reinforcement learning and imitation learning were used for playing test-based games. However, training a reinforcement learning methods or imitation learning methods normally needs a lot of data, and training is also expensive to some degree. So here we want directly use large language models as agents that can do symbolic reasoning. So we design a large language model agent with prompting. Then we use actions to trigger the symbolic module, and then given natural language description, for example, a natural language description of a math problem, our large language model agent can translate natural language to symbols, and then with the symbols, the agent can use symbolic module or tools. For our method, there are three main components: role initialization, action query, answered by the large language model agent. So for role initialization, we initialize the role and provide the instructions for the agent. We directly assign the task to the agent, and then this process informs the agent about its role and the task description and actions it can take, along with their explanation and constraints. For the action query actually is a repeated process at each time step. We prompt the large language agent with the current observation, inventory states, valid action set, and the question. And then for the answer, the large language model agent choose the action from the validate set, action set, to complete the task. In addition, it's also essential to develop appropriate prompts that efficiently constrains the agent's actions. Here are some examples. So you can say these constraints actually handcrafted. So in the real case, yes, they are handcrafted. So we found that it's not feasible for the agent to acquire all the knowledge and infer the rules just within the test-based games, just using trajectories from the games. So that's why we provide knowledge, actually human knowledge directly for some corner cases. And we manually define, we don't define a lot of rules. We just define some basic rules for the agents using the human knowledge. So let's see some results. The results show that our large language model agents actually has comparable performance with other approaches, especially with the imitation learning methods, behavior clone transformer. However, our large language models agents, is just based on prompting. There is no training. And we can also say that our on the left, our constraints also works very well. So as I mentioned before, there are a lot of corner cases, right? So we still need some human knowledge to help large language model agents to finish a task. And on the right, we can see that we use GPT 3.5 and GPT-4 as the backbones of the agents. Individually, you can see that if we use GPT-4 as the backbone of our large language model agents, it works better than using GPT 3.5. Now, I'd like to summarize my talk. We can see that language agents can work with logic graph. So in the real world, we have a lot of applications to based on logic graphs, right? So for the language agents, it can also work with logic graph. And language agents can leverage language models. So we have a lot of large language models. We also have some medium size or small size of language models, right? These language models, especially not large language models, are also has a lot of knowledge, maybe from experts, maybe from some specific data sets. The language agent can use these models. And lastly, we also show that large language models can be considered as a neuro-symbolic reasoners. Actually, it has great potential to perform symbolic tasks or tools in real-world applications. Thank you. Any questions?
So I just trying to understand what your sort of research question is here. What does it mean to be a symbolic reasoner? And I know that sounds like a stupid question, but you said earlier that if you use the symbols can be used to represent entities in the world, but I guess a word in natural language can be used to represent an object in the world, like an entity in the world. That's kind of the point of words. So is language, the use of language, symbolic reasoning? What's the distinction between using natural language and I guess you have a very narrow definition of symbolic reasoning that I don't really understand. So I'm asking you what that definition is.
Thank you for the question. Imagine that if you use calculator, right? So here, for example, if you use calculator, you cannot provide a language to the calculator, right? You can just type some numbers and an operation like plus or minus. So it's like here, the div 22, 11. So these symbols are the basic of the symbolic reasoning. So the symbolic reasoning here in my work is translate the natural language to symbols, and then the symbols can be used by the utilitarian tools, because some utilitarian tools cannot process language directly.
So your definition of symbolic reasoning, I'll just shut. Your definition of symbolic reasoning, are you constraining it to some kind of formal language?
Yes.
Non-natural language?
Yes.
So you don't regard natural language as manipulating symbols?
Yes. So it's like,
right, but in that case,
it's like
but I can ask
function, right? So if you write a program, so it's like function. So function, for function, it has predefined format of input, right?
So if I ask GPT-4 to add up, no, to divide 22 by 11, is that symbolic reasoning? Because if so, isn't the answer to your question trivial? Clearly, large language models can do symbolic reasoning.
Yes, yes. So that's my work also demonstrates that the large language model can do symbolic reasoning.
But isn't that a trivial conclusion? We know that large language models can do symbolic reasoning if you just need to type 22 divided by 11 into GPT-4 and it will tell you.
So my answer is yes or no. So for yes, yes. You're right. For no is that if you directly use large language model for example, for a random task, you cannot have the like symbols translated by the large language model easily. So that means you need. That's why we have prompting engineering here. So we need to have some prompts to guide the large language models to do the symbolic reasoning.
Thank you for your talk. I'm very interested in this area, although it's not directly related to my research. I guess you're familiar with Voyager, the LLM-based agent model that Microsoft came up with for navigating around Minecraft. They're kind of using code as sort of semantic waypoints that would be maybe analogous to the using symbol ontologies like you have here. I'm just wondering, because I mean the problem that you're solving in terms of these the text-based games, I think this approach really shines in this sense because you're acting in this relatively constrained space. But what do you think, if anything, you would need to change in order to make this sort of model work in a more open-ended setting like Minecraft, where it's very much about aligning with the human imagination of surviving in the wilderness as opposed to this sort of call response environment that a text-based game adds? Or do you think it would just work?
What a good question. Thank you. I know there are a lot of works working on Minecraft, and then they also developed large language model-based agents for solving complex tasks, right? And so I think my work, as I know, for these works, so they develop models or methods for agents to finish tasks in Minecraft. However, they didn't use external tools within Minecraft to finish some tasks. So the reason maybe is that they didn't develop some existing benchmarks that using within Minecraft using external tools. So I think my work also give a hint for the Minecraft researchers. Maybe they can develop some environments that need the external tools, right? Maybe easily they can include the symbolic reasoning within our tasks.
Yeah, I certainly think there's a reason to consider that it might be additive to have both the sort of API that is providing this sort of highly dense semantic context for the task that it's doing, along with some game symbol ontologies and so on. But I mean, do you think that your approach would sort of map to it, or do you think that there would be things that you would have to do to make it work?
I think my work can be applied for the Minecraft environment. So I agree that basically in Minecraft they use code, right? So it's somehow it's like they also use the external tools like the compile, right? The Python compile, right? Here my work is more general, so we want like other tools like the calculators, even the Google Map or other tools. So I think we have similar ideas, and so I think code has its advantage. Maybe the code can be run very fast, can have immediate action. However, here our work can use any external tools, but the disadvantage here is that we still need some manually design the prompts to connect the natural language part and the other side external tools. Thank you.
We have two questions. First of all, the symbolic logic. Presumably you're representing some mathematical logic, modal logic, temporal logic, second order logic. What logic are you representing the symbolic part? And the second question is on the graphs. The graphs obviously are dynamic, but there's a temporal nature to the interaction world. So I go into the environment, it rains, it stops raining. It's not just that I'm learning more things about the environment, so it grows, the knowledge you have grows, but there's a temporal component to things as well.
Thank you for first question. Very good question. Very professional question. And so in our work, we don't consider the logic part of the symbolic AI. So we just consider the symbols of the symbolic AI. So we simplify the problem. So you can see here. The main work is that we translate the natural language to symbols. So after that, we don't consider the logic of the symbols because our tool is quite simple.
The symbols part is there's a symbolic representation, but what you codify into some mathematical language, modal logic, second order logic, predicate logic. What's your representation? That's the question. I understand symbolic part, but what are you codifying that into?
For example, if the mathematical problem is a geometry problem, right? You need to prove something. So we can also translate the geometry problem into a sequence of the math symbols. So then we can use external like geometry math tools to solve it. So, but here in our games, because we don't have very complex mathematical problems, so we just have like the arithmetic problem, right? So that's why we use a very simple case to demonstrate the potential of using more complex mathematical symbols, or even like you mentioned the symbolic logics, right? So this is we just use a simple problem just because current game just supports a simple mathematical problem, but I think it has potential. Yeah. And for can you repeat the second question?
The second part was more on the graph. Obviously, dynamic. You're interacting environment. You learn more about the environment. But some components are temporal. I go out in my environment. It rains, or there's an enemy that comes and goes. So that isn't a fixed element of the environment. It's dynamic, in terms of there's a time component to it. Somebody there and goes, so the environment changed. So how do you represent that in your graph?
So in our work, the knowledge graph actually is also dynamic.
No, I understand. But so the graph is I'm in point A. There's a mountain on the left hand side. So there's a mountain thing comes up. There's a tree. There's another tree. But then it rains and then it stops raining. That's not a fixed It's not a fixed, it's not a fixed component. It's not something I've learned. I've interacted with environment. I learn more about the environment. So my knowledge grows. But there's some components which are come and go. So let's say I've never played a text game, but enemy comes in and disappears.
Yeah, I can understand, but I'd like to show an example. For example, for agents, it has a connection. It has a connection to an Apple. So maybe the connection is just the agent has an Apple, but later the agent eats the Apple. So I think in your case you mean the Apple disappears, right? But in our logic graph, so the relationship changed from had to eaten. So this is how we represent some dynamic or changeable objects.
This is slightly related to the previous question, actually. I wanted to validate my understanding of this. When you're talking about symbolic reasoning, I hope this question makes sense. Is this the same thing as, well, effectively function calling within large language models? So GPT-4, most of the endpoints of GPT-4 can natively support function calling. And what it's effectively doing there, as I understand, is symbolic reasoning. So it understands a problem as a mathematical problem. So you've got the kind of built-in Python API within ChatGPT, for example. It understands it as a mathematical problem. It formats that as JSON. So my understanding is that that is symbolic. It's codifying it symbolically as JSON so that it can then pass it into a module, which computes that JSON, returns an output, and then the large language model receives that in its context window and can process it. Are we talking about the same thing here?
Thank you for the question. For me, I think similar. But in symbolic AI, it has its specific formats. So it has its own system to define symbols and objectives. So and relationships. So I think similar. So large language model can translate the language to code. And here in our work, we translate the language to symbols, and then we use the symbols to use external tools. So maybe the external tools is a API, is a function, is run by a Python compile.
And those modules, how are they ingesting those symbols and processing them?
So the module here is more like a black box. So it's like existing developed tools. So we just provide input. So like a UI here. Yeah, you can say it's similar to the function, right? And then the black box tool just return the answer.
And that black box is programmatic. It's not a machine learning tool.
It's a programmatic. Yes, it's developed by other programmers.
To follow on from that question, if the modules are being invoked effectively via function calling, and in this example, that's doing division or the multiplication or whatever it is the large language model doing the symbolic reasoning, or is it just invoking, as you say, a black box that then does the symbolic reasoning?
So can you repeat your questions? What's your question?
So
I agree with you.
So the title of your talk is Large Language Models Can Do Symbolic Reasoning.
Yes.
Right? I suppose my question is, in this particular example, is it such that the large language model is doing said reasoning, or it is actually invoking another tool that is effectively doing the reasoning?
Thank you for the question. So my answer is the results from my work show that large language models has a capacity of the symbolic reasoning. So for example, So when we humans, we communicate with each other. So if we face a mathematical problem, maybe we understand it rather than we use calculators. So similar, our work shows that the agent interact with the test-based games, interact with the test world. Then the agent now observes there is a mathematical problem. So one solution is that large language model can also solve some mathematical problem, right? So large language model, if you use ChatGPT, you can directly input the mathematical problem, and then ChatGPT can return some answer. Maybe the answer is not accurate. Currently, is not for some cases, it does often returns some wrong answers. However, our solution is second solution. So the agents just understand, oh, this is mathematical problem. And we also already gave some information about existing tools. So the large language model can connect the math problem to the external tools, which here we use symbols. So that's why I'm confident that for maybe our problem is quite simple, right? For our problem, yes, the large language model can demonstrate their its capacity of the symbolic reasoning.
Thank you.
Thank you.
Okay, thank you for the talk. In your when you touched on knowledge graphs, you were using graph neural networks. When have you done anything on using the knowledge graphs with external LLMs where the knowledge graph is not embedded in the model, but it's a module that's being communicated with? And in which case, what considerations have you had for getting the language model to link up the entities that it's talking about with the actual entities in the module of knowledge graph?
Thank you for the question. I think it's a good suggestion, but currently, I should say, our work using large language using knowledge graph, this work is around 2020. So before ChatGPT, before large language models. So I think in the future I will try. I think that's a good suggestion, and my guess is that it's possible, right? I think if we have a appropriate way to encode the knowledge graph for the large language models, maybe if the large language model agents can process the task.
Thank you.
Martin, can I suggest one last question from someone at the back? Is that what you were going to say? Oh, you were going to ask another? All right, then. But this person's had their hand up a while.
It's my fault for sitting way in the back. I actually wanted to ask a question about your morality policy or morality term. I guess, like, I agree with the goal to not train immoral agents, but is modifying effectively a reward function here in this way like the right way to go about it, or is the problem that with the model learning to take immoral actions the fact that your like training situation or the game is rewarding kind of behavior you don't actually want your model to do, right? I think someone asked during the talk about the fact that it seems like from your graph, human experts are significantly more immoral than any of the agents, which sort of suggests that, like, I mean, unless we think those people are just terrible, that probably the game itself is maybe not like a good situation for training moral behavior, and maybe you would want to create like a different world to learn the right kind of actions rather than add a new policy on top to try and modify the underlying problem with the reward that's being generated. Does that make sense?
Thank you for the question, and my answer is yes. So this is as I mentioned in the talk. So we found that actually this is issue of the games. So you can say, we humans develop a game. However, in a game, the game does not give a penalty for immoral actions. So, based on the game, we consider based on the game, we collect data from the game, and then we found that some actions, observation action pairs, are immoral, and some actions are good. So we actually use external human knowledge here. We say the common sense prior or the common sense pre-trained model to give judgment for the actions of the agents. So I think in the future, for game developers, maybe you need to maybe they need to develop some rules to provide penalty for immoral actions, or they can use external tools, or for if we develop agents, so we consider internal knowledge to help the agent make moral actions. Did I answer your question? But you still need to have the information about the morality, right? Because morality actually is for me is a high level concept. For different countries, for different cultures, they have different definition of the morality. So actually the morality is kind of a human feedback. So we still need the knowledge about the morality.
Meng, do you mind a couple more questions, or do you want to finish? It's up to you.
I can accept more questions.
Okay, I'm going to ask a quick one. So you said, I think in the paper you say that you're introducing, in the neurosymbolic work, you're introducing the use of large language models to do symbolic reasoning. But this work seems very reminiscent of the tool former work from Meta AI, who also gave a talk at the Meetup last year. Would you be able to place this work in context with that work? So in that work, they use large language models to make calls to calculators and also to translation tools and just other tools, which I think, I'm not sure whether you would agree, but it seems that those are very similar kind of tasks to this work.
So my answer is yes or no. For yes, they are similar. So here we also use tools. So I think there are already a lot of works that use prompting to use external tools, right? But here, the games we address, the test-based game we address is a simple game. I agree. However, we want to demonstrate that the large language model agents can understand symbols, can understand, can do the symbolic reasoning. So next, one of the attendees asked me a question. So can large language model consider the symbolic logic or even use very complex symbolic logics or symbols? So if just using, so for like you mentioned, for the meta, they just connect large language model to tools. However, if we can represent for example, mathematical problems with a lot of complex or a sequence of symbols, math symbols, then maybe we can do more complex symbolic tasks, not just a tool or a couple of tools.
Yeah, I suppose the first thing is more of a comment about the morality thing, which is that it seems to me that often by most metrics that you would want to measure, the optimal thing may not be the moral thing to do. So if you train in an environment where the optimal thing always is that, it feels like you're not really representing the kind of things that you would actually want to train, that it would actually be used in. And then the other thing was, have you you were talking about formal logic. Have you tried formalizing using LLMs to formalize sentences into formal logic? And if so, how accurate is it?
So what's your first question?
It wasn't a question. It was a comment on the on the previous one. But yeah, then the second one is about if you've tried formalization.
So for symbolic tasks, we use existing symbols. So here, yes, we use very simple symbols. We just use one tool, like for a mathematical rule, we just use one tool, like the calculation modules. So I think we here we don't define the format of symbols. So we just use the existing format of the symbol, and then we translate we use large language models to translate the natural language processing and the natural language to the predefined symbols. Did I answer your question?
It was. I was more thinking of. I was just wondering if you had tried that on, for example, translating things into propositional predicate logic, given a specific, here's a logical language and here's a sentence. Have you? I was just wondering if you tried a task like that.
Very good question. In my work, we didn't do demonstration, so we didn't provide some like pairs between language and the target's symbolic format. We just use prompting directly. Yeah.
Unfortunately, we're going to have to stop the questions. It feels like we could go on for hours, which I think is a sign of a really great talk. So thanks so much to the speakers.
Thank you, everyone.
And James from Meng Group is going to make a very quick announcement, and then we can go and grab some beers. If anyone wants to go to the pub, I've been told that the banker is just is recommended. It's just on the same side of the street. So join you for beers in a second. And just to say again, for the beers, we get some exchanges. So thanks, James.
Yeah, so new venue for the machine learning meetup, as Martin said, but actually, I guess Meng Group's been supporting your event for years. So pre-COVID, so some of you would have come to that, and it was actually in the Nomura building, which is that way, I think. So we're very happy to do that. We also support PyData London meetup, which is actually happening on Tuesday, which I recognise a couple of you from. So, and there's still spaces for the Tuesday one. I think it's a bit quieter because it's Easter. So do have a look at that. You have to go to the PyData London meetup page. So two takeaways from me, please. Thank you for coming. And please consider Meng Group as a place to work. It is a fantastic place to work. I've been here 13 years. It's incredibly open and collaborative, and a pretty exciting place to be. I don't think you'll find an asset manager, at least, that's more like that. Then we do lots of data science. So there's a whole range of things going on in there by the logos at the top, but it includes systematic asset management. So like very much data science, data, algorithmic, research-driven process, also discretionary and solutions businesses, but all very quant-driven. So we have roles across quant, data science and technology. So please take a look at that. And then a little pitch from me. I run ArcticDB within Meng Group, which is a data frame database that supports all of the data science and all of the market data and all of the alternative data that we use. So if you do Python and you work with data frames and you just want them to get them back and into Python and out of Python as quick as damn possible, without having to run complicated infrastructure, then this should be attractive. So please take a look at that. And with that, thank you. Beers and pizza. Pizza's been sitting there a while now because of the questions, but hopefully it's still warm. We have to be out by 8. Anything else, Martin? Thank you.